My dear friends, welcome to Rajashekhar classes on applied data science with Python. This is lecture number 457. In this lecture, we will try to understand isotonic regression or calibration. So, now we will understand the isotonic regression, which is very popular technique which works even if your calibration plot does not look like a sigmoidal function. Actually, it is very beautiful idea. The way it works as, let's assume I have my average y cap of I on x-axis and my average yi on my y-axis. This is what I have. Now when I plot the data, I am actually plotting my calibration plot. Let's assume the data looks like this. This is roughly looks like the block curve that we saw in the previous lecture. This is how block line looks like. Just try to refer my previous lecture where you can see this type of curve. So given this, simple sigmoidal function will not work because a sigmoidal function will looks like this. Just see this one. A sigmoidal function will try to fit something like this, which means think of this like a regression. Just think of this like a regression problem. This is being your xi and this is being your yi, isn't it? And you are trying to find a function that maps from xi's to yi's because your decalibration data, as we have seen, contains y cap of I comma yi. If you think y cap of I is, if you think y cap of I as xi and this is yi on x-axis, I have yi as yi's. This one. Just observe this particular graph. What it says. Just see. This is I am assuming this as my xi and this as my yi, isn't it? If you think y cap of I, this is y cap of I as xi and this this one as my yi, isn't it? Yes. Now what is this? What does it mean? We are trying to find a function g. I can say we are trying to find a function g that maps from y cap of I to your yi's. That's what we are trying to achieve, isn't it? That's what we are trying to achieve. This is your sigmoidal function. This is your sigmoidal function. It looks like this, isn't it? You are making lot of errors. Just observe. You are making lot of errors. Just see here, I can see the error. Here this is error, isn't it? You are making lots of error. If you think of this as a curve, if you think of this as a curve that can fit, this is a curve that can fit. You are making lot of errors here. All these points are very far away. These are the points. These into marks are points. These are very far away. But what is the solution? Very elegant solution. Let me redraw this. This is yes, and this is my average. What is my average? Y cap of I, isn't it? And this is my average yi, and my calibration plot looks like this. It is like a stepwise function, isn't it? This is like step function. The core concept of isotonic regression or isotonic calibration, it says that let's break up this whole curve into multiple linear models. So I can fit a line here. Just see, I can fit a line here L1, isn't it? This is almost like a line. Just observe this one. This is almost just like a line, isn't it? This is almost like a line. What if I fit a line L1? What I fit a line L1 here? If the other line here, let me say this is other line, let me say L2 here. If I fit another line L3 here, if I fit another line, I can say L4, this is my L4, and if I fit another line, that is L5 here. So regression tries to achieve. So what's happening here? So isotonic regression tries to achieve, it tries to approximate this relationship using a bunch of lines, and these are called piecewise linear models. These are basically, what are this? Piecewise linear models, because you are taking a piece of total curve and you are building a linear model here. So in this piece L1, it is linear model. In this region, in this region, what's in this region? I use line 2. So what isotonic regression is saying, is I can't simply approximate this relationship as a sequence of lines. Here, let's say this value 1, just say this is value 1, and this is value 5, and this is value 7, and let's say this is value 10, 11, even let me say this is value 16. Let's say if my YQ hat, let me say if my YQ hat lies between 1 and 5. Your YQ hat lies between 1 and 5. Let me assume, let's say, use line 1. If your YQ hat lies between 1 and 5, which line I have to use? I must use line L1. So what I am trying to predict here, once I fit this curve, I will get an YQ hat, and I need to predict my probability, isn't it? What is this? Probability of YQ equal to 1 given XQ, isn't it? I have to, what I have to do, I have to predict the probability of YQ equal to 1 given XQ. That's what I need to predict, isn't it? Given YQ hat, I need to predict the probability of YQ equal to 1 given XQ. That's what I need to predict, isn't it? What is this? This YQ hat is on x-axis, isn't it? And this probability of YQ equal to 1 given XQ, this is on y-axis, isn't it? So given this is on y-axis, this part is on x-axis, isn't it? So given any point on x-axis, if this is, let me say, if this is my YQ hat, let me assume if this is my YQ hat, for a query point, I need to predict its corresponding probability value, isn't it? How do I do it? First, I will check YQ hat lies between 1 and 5. Yes, I will check whether YQ hat lies between 1 and 5. If it lies between 1 and 5, if your YQ hat lies between 1 and 5, I will use the equation of this line. L1, isn't it? This is like linear regression, where your input is one feature or one variable, output is also one feature. If YQ hat lies between 1 and 5, I will use this equation L1, line L1, to find the corresponding probability. Similarly, if YQ hat lies between, let me 7 and 10, let me say this is, if your YQ hat lies between somewhere here between 7 and 10, let's assume it's lies here, then I will use which equation I have to use. I must use line 3, isn't it? I must use line 3 to find the corresponding probability value. Now your question might be, how do we determine these lines? How do we determine these thresholds? What are thresholds? Let me say these are threshold 1, 5, 7, 10, 11, 16. How do I determine this threshold? How do I determine these lines? These are called these numbers 1, 5, 7, 10, 11. All these are called thresholds, because we also need to determine where this line starts. Where this line starts and where this line ends. Where is it is starting and where is it ends. That's what we need to find. That's what we need to find out. So the core idea is, again, it is an optimization problem. Basically, it's an optimization problem. I want to minimize the gap. I want to minimize these gaps. Actually, these, what is this? These intos are my data points, isn't it? I want to minimize these gaps between the predicted value and my observed value. What is my observed value? This into marks are my observed values. If you think about regression stands point of view, I want to find these thresholds. What are these threshold? 1, 5, 7, 10, isn't it? These thresholds are often written as A1. How will you write this? One A1, this threshold, one people used to write, this is A1 and this is A2, this is A3, A4, A5, A6, isn't it? These thresholds are often written as A1, A2, A3, A4, A5, A6. If a query point lies between A1 and A2, isn't it? And you need to use equation of line L1, isn't it? Let me say, what is my query point? Let me say this is my A1, isn't it? That's what it says. Let me say this is my A2, isn't it? If your query point lies between A1 and A2, you need to use the equation of line L1. Equation of this line, it's just a two-dimensional line. It is a line in 2D, only needs its slope and intercept. Y equal to mx plus b. You need m and b, because what is the equation of the line? Y equal to mx plus b. So if you have slope and intercept, you can represent line L1. So eventually we need to come up with A1, A2, A3, A4, so on, and corresponding regression lines. For example, between A1 and A2, between A1 and A2, what's happening in between A1 and A2, there is a line L1, isn't it? In this line L1, there is a slope M1 and intercept B1. Similarly, there is a line here L2 in between A2 and A3. For this line L2, there is a slope. What is my slope? M2 and intercept B2, isn't it? For line L3, there is slope M3 and intercept B3, so on and so forth. The whole optimization problem tries to find your thresholds. What are those thresholds? This whole optimization problem tries to find threshold A1, A2, A3, so on, A4, and the equation of the lines L1, L2, L3, so on, isn't it? Equation of the lines such that these points, what are those points? Such that these points, which points? These points, these into points, these are the points, these points, yes, such that, let me say, these points, these are the points. I will repeat, the whole optimization problem tries to find your thresholds and the equation of the lines such that these points, these into points, these are the points of the decalibration. These are the points from decalibration lies on the lines as close to as possible. These points are as close to as possible to the line. At the same time, it also tries to solve. It also says, I don't want to have too many lines. I want to have just enough lines, because given any function, if I have, let's say, 1 million lines, 1 million lines means I should not have too many lines, isn't it? Too many lines are not advisable. If you have 1 million lines, if I have 1 million lines, then that's not right thing. That's not right thing, isn't it? I may be okay with 10 or 15 lines. So optimization problem tries to find your thresholds A1, A2, A3, A4. Optimization problem tries to find your thresholds and the slopes. So what is slopes? M1, M2, so on M3, and intercepts B1, B2, so on B3, and intercepts slopes and intercepts of these lines, while putting a constraint, enforcing constraint that there should not be too many lines. It is a straightforward optimization problem. This optimization problem looks like extended linear regression. I can say this optimization problem can be extended. This is extended linear regression problem. There is one catch with isotonic regression. With isotonic regression, you need many more points than with your plot scaling, isn't it? I will repeat. With isotonic regression, you need many more points. You need many more points. With isotonic regression, you need many more points than your plot scaling. In plot scaling, you have two parameters, A, B, isn't it? In the plot scaling, we have two parameters, capital A and capital B, that we have to determine. In isotonic regression, we have thresholds A1, A2, A3, so on, isn't it? And each of these lines, L1, L2. So you have more parameters to estimate, which means you need more data. You need more data in the case of isotonic regression. More data or more points, more data in decalibration. In the case of isotonic regression, you need more points in decalibration. So if you have large data, then you have large cross validation. large cross validation, then you can have large decalibration. When you have large decalibration, we can apply isotonic regression. When you have large decalibration, you can apply isotonic regression. If you have small decalibration or small cross validate, then it is better to use simple plot scaling. Just go through this lecture. If you have any difficulty, please keep a comment. Thank you very much.